right, so we're looking at, what was the reaction we're looking at? Number 90, do you have the reaction? Actually, did we set it up? Did we already set up the K expression?
Yeah, we did.
Okay, then we're just trying to solve it. Okay, then we were talking about the other technique. All right, let's take a look at that. With these ice table problems, you run into trouble quickly with the math, and that happens frequently. And so we have to learn little tricks to make the math a little easier. And so this is what we were doing yesterday. So 2Fe3 plus Hg2 2 plus. This is going to give us 2Fe2 plus 2Hg2 plus. Okay, and then Kc for this is given 9.14. And so we reset this. So what was the bottom line? This was 0.5300 minus 2x molar. It was 0.5150, actually 0.5300. No, 5150 minus x molar 2x molar. And so we know the Kc is 9.14 times 10 to the minus 6 is the ratio. And so this comes out to 2 times 4x. Actually, we'll just do 2x squared times 2x squared divided by 0.5300 minus 2x squared by 5150 minus x. So I'll just rewrite it over again. And so the situation becomes, what's your first x going to be? So I asked you to solve this. But solving this sometimes will take a long time if your initial x guess is way off. And so we try to guess an x value. Well, what's the x going to vary from? What will the x vary from? Well, what's the smallest x we can have? According to our second ice table here. The smallest x would be 0. What's the biggest x we can have? No, because the biggest x, well, it's going to be this. We can't let this go negative. And so 0.5150 is too big, because that would be 2 times 0.5150, which would make this go negative. So it's going to be half of this. Half of this would be 265, 0.265. And so it would be between 0 and 0.265, you just take a guess there. But what we can do is, we tried 2 techniques. These are techniques that when you get stuck, and you will get stuck. You'll get stuck and then you'll think, okay, what can I do? Well, one thing you can try to do is the first one, which was reset. And the second one you could try to do is something called the simplifying assumption. The simplifying assumption is discussed more thoroughly in chapter 16, but we need it for chapter 15 too. And the simplifying assumption just says that the change is small. Change is negligible. If the change is negligible, then we can ignore the change. Therefore, ignore the change. But we don't completely ignore the change. Ignore the change initially, and then factor it in later. then factor in later. And so initially we ignore it, and then we go, oh, okay, we better not ignore it. So there's something not right about it, and it's true, there is something not right about it. The simplifying assumption is going to introduce error, for sure. And what we do with the simplifying assumption in this particular example is this. This is what we call the change. This is our initial. This is our change. This is our initial from the ice table. This is our change. You know, but I didn't write them down because I want to save some time. You should have these in your notes. Do you have them in your notes? The ice table, hopefully. Your note. Okay, so we have the initial and the change. So what we say is the change is negligible. What that means is we can ignore the change. If we ignore the change, then what happens is this. If we assume change is negligible, then what this is okay, 2 squared is 4, 2 squared is 4, 4 times 4 is 16, this is going to be 16x to the 4th on the top. And then what we're going to say is 0.5300, and if we could ignore that change, then it's just 0.5300, you know? And how can we do that? How we can do that is we look, you know, is there going to be much water flowing to the left to right in this scenario? In other words, when we're thinking about the water well, you know, if you look at the ratio, what does this ratio tell you? Ratio tells you it's all reactants. Actually, I'm going to, right now I'm just going to, I need to do some catch up here, so I'm just going to continue on with this. But the ratio tells you it's all reactants, so that means very little forward reaction should occur. And so that's okay. However, if we were going backwards, then this would not be a decent assumption. So this is a decent assumption because K is small. The K is small, we expect very little forward reaction. Now the same thing happens here. We're going to say that the change is negligible. One way of thinking about this is if you have a swimming pool, we'll consider this a big swimming pool stuff of matter. And if we take just one drop out of the swimming pool, is the change in volume significant, or is the change in volume negligible? You know, yeah, nobody would get upset that, you know, somebody splashed some drops out of the swimming pool. They wouldn't go, oh my God, some drops are missing out of the pool. No, and so this is the same thing, you know. But how do we know? I mean, 0.5300, is that a swimming pool's worth of matter, and X is a drop? We don't necessarily know. We're just taking a guess because of this small ratio here. And if we do that, then solving for X is simple. We could solve for X. It would be pretty easy to do. We could not forget the square here. And so it would just be 9.14 times 10 to the minus 6. 9.14 times 10 to the minus 6 times 0.5300 squared, so times 0.53 squared times 0.515 equals, and then divided by 4, or not 4, 16, divided by 16. And then what we'll do is we'll take the 4th root of that. And so I'll just raise this to the 1/4 power, or the 0.25 power. And that gives me X equals 0.0169. We're allowed 3 sig figs, so we carry 1 extra, 0.1695. Now, this we said is negligible. Is it really negligible? You know, this is not correct because this answer, you know, is based on making this assumption. But what we can do is we could see, you know, what kind of percent change was that? And so if this is X, then we can calculate the percent change based on this, which is not entirely accurate, but it's going to be somewhat close. And so this is going to tell us. And so for the 0.5300, the percent change is going to be 2x over 0.5300. times 100%. Okay, that's for the iron. For the other one, it's going to be x over 0.515 times 100. And so we look, and so in the first term here, the percent change is, okay, I'm going to multiply this by 2 times 2, and then divide it by 0.53 times 100, and that gives me a point change of 6.398%. Okay, then we'll do it on the bottom one here. The x is 0.1695 divided by 0.515 times 100. 3.29% change. Now, it's one thing, 3.291 actually. It's one thing, let's say, to lose a drop of water. But let's say, okay, if somebody, you know, a drop of water splashes out of the swimming pool, there's no change. But if somebody takes out 6.4% of the water, would anybody notice? If one day the swimming pool was missing 6.4% of the water, would anybody notice? One day your bank account's missing 6.4% of the balance, would you notice? Let's say okay, a penny, your piggy bank is missing a penny, would you notice? Probably not, you know, penny is not that significant, right? But if you're missing 6.4% of what you had in there, would you notice? Yeah, I hope so. I hope you'd notice. But the situation here is this. What constitutes a negligible change? 6.4%, I don't think is a negligible change. I think that's significant. If you had if you had 10,000, let's say, or 100, if you had 100 gallons, you know, you'd have 6.4 gallons missing out of 100. If you had $100, that'd be $6.4 missing. And so this is starting to seem significant. And so what we want to see here is, we want the percent change to really be negligible. If the percent change were like 0.001%, is that really significant? If you lost 0.001%? So if you had like $10, it'd be like a tenth of a penny? No, that's not significant. And so what we're going to do is we're going to come up with an arbitrary cutoff. This is going to be an arbitrary cutoff. The arbitrary cutoff is this. Greater than 5% is too much. Therefore, too much change. Therefore, the simplifying assumption is not valid. You know, because anyway, this simplifying assumption is based on well, I'll just call this. The simplifying assumption is based on introducing error into the calculation. So this number is not accurate, but you know, ballpark, the real number is going to be like that. And so if it's greater than 5% change, it's too much, and therefore it's not valid. And so this is a greater than a 5% change here. And so this is not our x value. And so we are not going to use, we will not use x equals 0.01695. We will not use that x. But this is a good first, guess. And so we're trying to figure out what's, we're going to do the guess and check method, or the method of successive approximations. So what is a good first guess? Well, this is a good first guess. Because, although it's not good here, this will help us in solving this. And so what we'll do here is that it's too many sig figs for our first guess. And so what I'll do is we'll just go 0.017. How about that? And so we must use this method of successive approximations. And so simplifying assumption, I'll abbreviate SA, but successive approximations I won't. I need some other SA for that. And so this failed, but what it did do is it gave us some X value to get. And so what we're going to do is we're going to guess X and then solve for K. And so our first guess is going to be 0.017, because we don't want too many sig figs in there. And so we'll just plug in 0.017 into this, and then calculate our K value. Now, repetitive calculations like this are best done in Excel, And so if you guys have Excel at home? If you have Excel at home, what we normally do is we just set up a table like this, and then we'll just put in X, and then over here we'll put in K like this. And then what we do in Excel is we type in a formula for K. And so the formula I'm going to type in is equals. And this is going to equal, equals. Now I'm going to go with 4. Actually, no, sorry, I got this wrong. 4 times 4, yeah, 16x to the 4th. And so what I'll do is I'll just type in 16 times x. X is a, and then we're going to raise that to the 4th power. So we'll raise it to the 4th power. So, this would be a2 raised to the 4th power. And then we'll divide this. I'm going to divide this by 0.5300 minus 2x quantity squared times this. And so I'm going to put another set of parentheses around here because I need to divide the whole thing under that. And so I'll put in 2 sets of parentheses like this in Excel. Oops. And so now we're good here. And so I'm going to go 0.53 minus 2 times x, which would be cell A2 here. Okay, and then close the parentheses times, then parentheses 0.515 minus x. So this is going to be minus A2, cell A2, and then close both those parentheses. This would be the equation. This is what you can do at home to speed up your homework. Unfortunately, you can't do this on exam. On exam, you just have to grind through it, by a calculation. And so what I'll do here is I'm just going to copy and paste this formula down. So right now we don't have any x values. So the first x value we guessed was 0.17. And so of 0.17, oops, not 0.17, 0.017. 0.017. The first x value, we come up with 5.41 times 10 to the minus 6. 5.41 times 10 to the minus 6. Well, it's too small, right? And so what should we do? Should we guess bigger? Yeah, let's guess bigger. So we're going to guess bigger, 0.018. 6.84.
Professor?
Uh-huh.
I think you forgot the square for the 0.53.
Oh, did I? Let me check. Oh, yeah, you're right. Let me square this here. Thanks. Catching that. So this is going to be squared here. I'll just copy this down. Okay. This is times 10 to the minus 5. So times 10 to the minus 6, we're too big. Do you see? So this would be 13. This would be 10.9 times 10 to the minus 6. This would be 13.8 times 10 to the minus 6. So we're going the wrong direction. Do you see we're going the wrong direction here? So I'm going to drop it down. I'm going to go 0.016. We go 0.016, we're at 8.47 times 10 to the minus 3. So we're getting a little closer. So this is the way I look at it. In fact, I'm going to let me delete the 0.018 just so to make a point here. I'll delete that row. And so we're going from 0.016 to 0.017. So we're going from 8.47 to 10.9. We need to go to 9.1. So that's about halfway between here. So this is about halfway between these. I'm going to go 0.0165 and see. But with Excel, we can do something very easily. With Excel, we can look at the whole series. So for example, with Excel, I can just go 0.0161 right? And then just do this. Oops. We'll just go with 0.0162. And then Excel will just do the series. So for example, I'm going 161 to 162. I'm going to have Excel do it all the way to 170. So let's go ahead and do it all the way to 170. Here. And so here, it just fills it in, and it just makes it a lot easier to do the calculations here. And so you can see, the next number I was going to guess was 0.0165, which would give me 9.63, which is close, right? But still off. And so I'm going for 9.14. And so that was too big of a guess. Take a look at here. You see? At 163, I have 9.15. At 162, I have 8.9 or 9. And so I need to go to 9.14, which is just about here. So my guess would be like 1629, almost 163, right? But with Excel, you could do this, of course, you could do this very quickly. What we could do is we could just go ahead and do 1.0169, what was it? 629? 0.01629, like this. And it's 9.13. Do you see it's too small? And so what I'm going to do is I'm going to do another series. I'm going to go 0.01691. Okay? And then with Excel, I'm just going to have it fill in all the way to 903. Oops, what happened there? I put a 3, no wonder. Oh, and I screwed up. I didn't need that. Okay, there we go. And so what I'm going to do is I'm just going to have Excel do the whole series all the way down here. Oh, it's okay, so let's fill in the rest there. Okay, so I know it's going to be very close to what did we say? 163. So it's like 1629. But you look at 1629, do you see that? It's too small, so I got to go bigger, or just, a little bit smaller. So just a little bit smaller. This series didn't work out, sorry. 16291. And then 16292. 6292. And so the power of Excel is it just saves you a lot of calculation. In fact, I could do this a lot quicker once, if we're just doing it just randomly, just this, but this is how you're going to do it. But once you have the strategy, then I would have just nailed it down quicker, because you would know what to skip it. But that's after you do it a couple of times. So here, where are we at? We want 9.14 here, 16294. And so 0.016294, 0.016294, and I have 9.140 times 10 to the minus 6 is a check. Now, take a look at this. This is the number. This is, the correct X value. We didn't make any assumptions, etc., to get this. We're just doing guess and check. And it's close enough to the number of sig figs that we want. Now, compare that to this number. Do you see? It wasn't terrible. The one we got from just guessing that we could ignore the change was 0.01695. But this is 0.0162. And so it's not, 29. It's not terribly off. Do you see? So this is a good first guess, and that'll get you in the target. If you have a bad first guess, then and then you start guessing too many digits, then you're all over the place, and it could take a long time. Because on a test, I saw one person took over 1 hour, because I give extra time. They just stayed over. They spent over 1 hour guessing X values, and they never got it. And you figure, if you spend an hour guessing X values, eventually you're going to get it. But their first guess was so far off, that that it took them so long. And so, okay, this is the rapid guess and check method using Excel, which you could do for your homework is no problem, but for a test, you got to remember you got to do it by hand. And so now we can calculate the equilibrium concentrations. And so 2 times 0.016294, okay, is equal to what? And so 2 times 0.016294 equals 0.032, 0.03258. These are significant because those are significant guesses. But we have to carry some extra digits here. So this is going to be 2, this is going to be 1, 4, 7, 0. Oops, let's screw this up. Let me check. Okay, this is going to be 10. Choose. 9. Well, probably should do it using my calculator. I have numbers in here. 0.049, 0.497412 molar. All right, and then we go over here. We can calculate the equilibrium concentration or mercury 1 ion, which is 0.5150 minus 0.016294. 0.016294. We'll just carry 2 extra digits there. So actually, let me do this by calculators faster than me doing it in my head. 0.515 minus 0.016294. And I got 0.498706. 06, those are not significant. Do you know why I carry extra digits here? It's important to carry extra digits when you calculate equilibrium concentration. And so this is the stoichiometry of the reaction. So a little bit of reaction takes place. You know, how much reaction actually took place? You know, earlier we calculated 6.34 or 398% change, right? That's the percent reaction that takes place. It's the one based on the larger percent change. And so this is going to be more significant here. And so the actual percent reaction is going to be this, 0.032. This will give me the percent reaction. The percent reaction of the iron 2 is 0.032588 divided by 0.53 times 100. 6.14. 6.148% reaction of the iron 3 plus. How much of this reacted? Well, it would be 0.016294 divided by 0.515 times 100, which gives me 3.163% of the mercury 1 reacted. Okay, and that's just based on the change, you know, how much of our initial was consumed here. So that's what we see. All right, how do I know that this is correct? Is there a way to check that I didn't make any simple errors? Is there a way to check that I didn't make any simple errors? Yeah, we plug it back into the K. This is called the double check. We double check. This is why I carry extra digits. I carry extra digits because I don't want round off errors in my double check, which might make me suspect a larger error. And so when I do the double check, I just plug it in. And so it's the iron squared, mercury squared divided by the iron 3 squared divided by this. So I'll just do this. These are the same, so I'll just raise that to the 4th power. And so 0.03258 to the 4th. Okay, divided by 0.4974. 0.497412 squared divided by 0.498706. 498706, and that gives me K equals 9.140 times 10 to the minus 6. It checks. And so we're good. This worked out. And so this was the equilibrium for this. And so what will the ion concentrations be at equilibrium? Well, that's what we see, the boxed ones there. Okay. Any questions on this particular problem? All right, that was supposed to be a challenge problem. Let's try one. Oh, wow, somebody always shuts everything down for me and turns off everything. Do you think you got it? You got it? Okay, we're going to try it. Do they have any no cards? We're going to just do it in class one. How about that? Do an in class one, number 74. Should be good. Number 74 is this ion. Do you know what the name of this ion is? Kelly should know the name of this ion. NH2 minus. No. Remember. It's because of that chart. Remember that chart there? Bottom right of the chart. No? Or does somebody know? Normally when you look at a chart, you look at the extreme. This is the first thing I do with the chart. And so the strongest acid is HCl4. You should know the name of that, hopefully. The name is Chem4. Perchloric acid. Wow, that took more time than I was hoping. It should be like immediate. This, for Chem 1B student, should be immediate. This is more like Chem 1A. Perchloric should be Chem 4. This is Chem 1A. Maybe you didn't cover it in Chem 1A. Maybe you never looked at this chart. You never looked at this chart. Well, you memorize the strong acids. So a lot of people in Chem 4 memorize the 7 strong acids. But do you ever memorize the strong bases? Well, most Chem 4 and most Chem 1A instructors is more like strong bases. But I made my students memorize this, but it's easy to forget, of course. What's the strongest base on the chart? Paul. No idea? Yeah, that's okay. No idea. But it turns out that this is called amide, or amide. As we would call it amide. It's the amide ion. What's special about the amide ion? The amide ion is an extremely powerful base. What other things are extremely powerful bases? Well, this is chapter 16, maybe. You guys didn't cover chapter 16 in Chem 1A. You're supposed to cover chapter 16, sections 1, 2, 7, and 8 in Chem 1A. This is why I was hoping I wouldn't have to review it. My plan was to skip those sections, but maybe not anymore. Which is okay, but I'm going to speed up things to go. So this is going to be plus H2O liquid. You know what bases do? Do bases ionize, or do bases do what? Did I talk about this? Bases do not ionize. Bases hydrolyze. So this is a base. This is what we call hydrolysis reaction. This is very common for bases. So hydrolysis reaction for base, which forms ammonia and hydroxide. Do you know what the strongest base that can exist in water is? The strongest base that can exist in water is hydroxide. Amide is too powerful a base to exist in water. So this is why we say that strong bases hydrolyze 100%, basically. But is that true? In chem, in like chapter 5, when we're talking about electrolytes, the strong acids, the strong bases, and the soluble salts are their strong electrolytes. But does this really hydrolyze 100%? You know, we assume it does hydrolyze 100% because that's what we learn in chapter 5. But let's use Chem 1B to figure it out, you know? Because it turns out it doesn't, because if it hydrolyzed 100%, then K should go to infinity, you know, because there should be 0 reactants left over. But is K infinity for this? No, in fact, it's huge. K is huge, it's 10 to the 20th, but it's not infinity. All right, so what we're going to do here is the equilibrium constant for the following reaction has been estimated if K equals 10 to the 20th. Actually, we could get it from there too. At 25 degrees C. Actually, you know what they say here? Because this is called the base hydrolysis. It's not written that way. In a solution prepared by dissolving 0.0125 moles of sodium amide in water to make a 1 liter solution. And so, what we have here is this is going on to chapter 16. Now, sodium amide. What would you call that? Would you call that I'd call it a strong base, but first off, I'd call it a soluble salt. What do soluble salts do? Soluble salts ionize in water. And so this is a soluble salt, and so it ionizes in water. And so, you know, if I had solid sodium amide, it would ionize into sodium ions and amide ions. Now, I wouldn't call this, you know, strong base. A strong base ionizes 100% in water. No, this is not. This is a soluble salt. The strong base part is the amide. The amide is a strong base, and what these strong bases do, they hydrolyze 100% in water. Because what would amide ionize into? Well, people try to ionize it into different things. And so what happens is the strong bases are all too strong to exist in water, except for hydroxide. And the same thing happens with the strong acids. The strong acids are all too strong to exist in water, so all the strong acids do is they hydrolyze water to form hydronium 100%, or they ionize 100%. And so this is the same type of scenario here. And so here, what we're going to do is we're going to prepare a solution of this. So if I have, in other words, this is going to be 0.0125 molar. So initial, here, I'm going to have 0.0125 molar, because if I have 0.0125 molar of sodium amide, it's a 1-to-1 mole ratio of amide to sodium amide. And so H2O liquid is a pure liquid. That means what we're going to do is we're going to assume nothing has hydrolyzed yet. This is what we always do. In a case like this, we just say, okay, nothing's hydrolyzed yet. This is what we have initially. Let's figure it out, what's going to happen. All right, and so why don't you do this? We have the K value. Why don't you tell me what the equilibrium concentrations are? In fact, they want the equilibrium concentration of amide. You know, is there any amide left over, basically? You don't really, you know, in Chem 1A, you learned in chapter 5 that strong bases hydrolyze 100%. Is it really 100%, or is it slightly less than 100%? And so let's do this particular problem, and then I want to see your progress. So I'm going to go grab some. I don't have enough here, but I need to replenish my supply of cards. And so this is